The title of this presentation is Open Boundary Conditions for the D23 Spin Chain in Sectors of Conformal Field Theories. To begin with the presentation overview, we'll be introducing the D32 spin chain, which is a model that shares connections at the intersection of the fields of quantum physics, statistical physics, and high energy physics theory. And we'll be describing how to encode boundary conditions in connection with conformal field theories, which are abbreviated CFT. And it's a very powerful tool and framework for being able to make different types of predictions. And we'll be highlighting how these the predictions in different sectors of the conformal field theory can be formulated from properties of the spin chain, and in particular from an asymptotic expression for a local Hamiltonian that we'll obtain. And in providing some insight into this framework and building up our intuition, we'll highlight differences between the higher and lower rank spin chains, because from the reference that I'll be discussing and alluding to, which is provided in the link in the bio, the authors list as one interesting prospect for future research that it could be possible to look how to encode open boundary conditions for the high rank spin chain as open boundary conditions have been encoded for the lower rank spin chain in previous work. And in doing this, we'll also be establishing connection with vertex models and other models of statistical physics. So when we provide an overview and a depiction of the sample rank or the sample space of the spin chain, we'll be discussing how it really has a lot of connections to the 6-vertex model and other vertex models, which relate to either imposing the ice rule or relaxation of the ice rule, which we'll provide a further overview of in a couple of slides. So first, we'll want to begin by introducing the R matrix and the concept of U1 symmetry. So the R matrix is the quantity that's defined in the first slide, and it's a parameter which is a function of U. And it's defined in terms of an exponential rescaling of the Jimbo matrix. And I provided the reference which explicitly defines the Jimbo matrix, but for our purposes, it's just informative to think of the Jimbo matrix as some matrix, which we can perform an exponential transformation of all the entries of this Jimbo matrix to obtain the R matrix. And the R matrix is helpful in the definition of the spin chain, as well as in the definition of the 6-vertex model, and in particular, even in the inhomogeneous 6-vertex model, because it satisfies the Yang-Baxter equation, which is given by the second item, the item in the second line. This is given by an intertwining relation in which we have in the left-hand side and the right-hand side of the equation, the R1 of 3 term remains constant, but we can interchange the direction or the order of the operation of the R12 matrix with the R23 matrix, in which on the left-hand side, we have R12, R13, and R23, whereas on the right side of the Yang-Baxter equation, we have R23, R13, and R12. And the concept of U1 symmetry comes into play with the R matrix, because the R matrix, it satisfies with respect to the commutator of the R matrix with respect to Hj tensor I plus I tensor Hj's vanishes. And sorry, I forgot to include the definitions for the Hj matrices, but they're just defined in terms of 6x6 matrices that either have zeros in all entries of the matrix but one, either the 1th entry or the 6th entry, and so on and so forth. And the spin chain has the following sample space. As we had just mentioned in the overview slide, this relates directly to the 6-vertex model. The 6-vertex model is another model that I'm not going to specifically discuss in this presentation, but I've given some other presentations on it in different videos on this channel. And there are many different types of aspects that one can look at the 6-vertex model. For instance, if you look at a height function representation, you can ask a lot of percolation type questions, which are raised by Dumino-Copan and his group. And one type of question that I looked at, in which they obtained a logarithmic delocalization result for flat boundary conditions, and they asked about how one would extend this logarithmic delocalization result for slope boundary conditions. On the other hand, if you look at inhomogeneities of the 6-vertex model, this is relating more to the construction of the 6-vertex model with the R matrix, in which one can introduce inhomogeneity to the model by looking at the spectral parameters which are involved in the construction of the R matrix. In this case, the spin chain, the D23 spin chain, is relating to the fact more towards the side of the R matrix construction of the 6-vertex model, because we can see that there are 38 possible configurations of the D23 spin chain. And the first 6 configurations are given by the sample space that precisely corresponds with the 6-vertex model. As I had also mentioned in the overview slide, the 6-vertex model satisfies the ICE rule, which is meaning that it's a conservation rule stating that there has to be the same number of arrows pointing inwards and outwards of each vertex. And we can see that for the first 6 configurations of the D23 spin chain, these configurations satisfy the ICE rule. However, in other configurations of this chain, namely the 7th and 8th configuration, or one can look as the 11th and 12th, or the 19th, 21, 22, 27, 28th configurations, they're satisfied, or they're constructed from the fact that there can only be 2 vertices or 2 edges, which are either pointing inwards or outwards from the vertex, and the other 2 edges, for the other 2 edges that are incident to this vertex, remain unlabeled. Or, as one can see also from the configurations which are labeled 9 through 14, there can be a mixture of different types of configurations from the 6-vertex model, which are also called line configurations, in which one can color bold the edges of the square lattice which are into vertex, while labeling the other 2 edges of the square lattice with some orientation, and so on and so forth. So this is just demonstrating that one can construct a much larger sample space for this spin chain that we're going to be talking about, and making a connection with conformal field theory with notions of the ICE rule, which are used to originally label 6 configurations which belong to the 6-vertex model. And this is to say that we don't have to stop just there, because there can even be the 8-vertex model, which is related to the 6-vertex model, except that one throws in 2 additional configurations. And this is related to a whole class of vertex models which relate to the spin chain and make it a particularly rich and interesting model for us to consider. And as we had mentioned earlier, we're going to be making use of the Yang-Baxter equation, because to encode open boundary conditions for the spin chain that we're going to be looking at, we'll also need to require that the boundary conditions also satisfy the Yang-Baxter equation, which, as we mentioned previously, is characterized by an intertwining relation. And to construct the higher rank transfer matrix, we need to keep the following into account. The transfer matrix is important because we're going to be able to define the monodromy matrix by taking the trace of the transfer matrix, and it's constructed by the fact that one can take a basis which is labeled from the elements 1 through 6 and take the tensor product of this basis with itself. And we're going to denote, to lighten the notation for the transfer matrix under open boundary conditions for the D23 spin chain, just as boldface T open of U. And as we have been mentioning, now that we're going to have the transfer matrix, we can construct the monodromy matrix and encode open boundary conditions into the transfer matrix with the K matrices. So we're taking a trace of a product of matrices, and within this trace operation that we're taking, we're looking at open boundary conditions, which is given from the leftmost position of the chain. And this is given by boldface K open plus of A of U. And then after we apply this K matrix for the open boundary conditions in the left-hand side of this product, we're also going to be taking a product of J from 1 to big L of R matrices, and then we're going to have another K matrix which is enforcing the open boundary conditions in the right position of the chain, which is also going to be multiplied by another product of L terms of R matrices, but instead we're going to have R minus of J prime of A of U instead of R plus A of J. And from the transfer matrix, one can obtain a normalized eigenstate, and it's important for us to obtain, or for obtaining the expression for a local Hamiltonian, to formulate an eigenvalue problem with these normalized eigenstates. The eigenvalue problem is given by the system of 2 equations, which is given by the set of 2 equalities that the normalized eigenstate satisfies. So we know that the transfer matrix applied to the normalized eigenstate is equivalent to the eigenvalues applied to the normalized eigenstate corresponding to the first equation of the eigenvalue problem. Whereas for the second equation of the eigenvalue problem, we're looking to obtain another equation involving the normalized eigenstate, in which we're taking Hj up, which is applied to the normalized eigenstate, which is equivalent to the eigenvalue applied to the normalized eigenstate. And we can provide a statement of the beta equations, which we're going to introduce now for the sake of completeness, but we'll also reintroduce it so that we can further discuss the root density approach to demonstrate how this approach that we're discussing with encoding open boundary conditions of the D23 spin chain is related to the fact that one can look at the density of roots of the beta equations and make a connection to the ground state of the spin chain of the D23 spin chain under open boundary conditions. And another parameter which is important to keep in mind when we're talking about the D23 spin chain is an anisotropy parameters. Anisotropy and isotropy, they occur in many different areas of math. For instance, in the 6-vertex model, one can look at isotropic parameters, which is performing a sort of a homogenization procedure in which we set certain parameters of the vertex model equal to each other so that we can obtain a simpler probability measure. In this case, the anisotropy parameter for the D23 spin chain appears in the fact that it's a parameter that comes into the statement of the beta equations. And even though we're stating the beta equations now with the anisotropy parameter for the root density approach, we're going to want to make a statement of the beta equations, which is for an anisotropy parameter that is very close to 0. So in the presence of this anisotropy parameter for now, though, on the left-hand side of the equation, the left-hand side of the equation of the beta equations is characterized by the fact that it's a ratio of a hyperbolic sines, and this ratio of hyperbolic sine functions is raised to the length of the chain L. And within each one of these hyperbolic sine functions, we're looking at the arguments being u1 of j minus I gamma, which is where I of gamma is the anisotropy parameter. And in the denominator of this ratio of hyperbolic sine functions, we're looking at u1 of j plus I of gamma. So it's a very similar parameter that we're evaluating the top in the numerator and the denominator of the hyperbolic sine function, where the u1 of j term is the root of the first type of the beta equation. On the other side of the beta equation, on the right-hand side, we're taking a product over k terms, where k is an index, which is introduced into the hyperbolic sine functions. But we have to be careful because the expression for the hyperbolic sine functions that we're having on the right-hand side of the equation of the beta equations in comparison to what's on the left-hand side of the beta equations is a little bit more complicated. For one, in the first term for the ratio of hyperbolic sine functions, we're looking at u1 of j minus uk of j minus 2 times the anisotropy parameter. And in the denominator of the expression, we're looking at the hyperbolic sine of u1 of j minus u1 of k plus 2 times the anisotropy parameter. So in this first term, from the ratio of hyperbolic sine functions that we're taking in the beta equations, we're taking the difference between roots of the first type of the beta equations for j not equal to k, so that this parameter that we're using for the hyperbolic sine for the difference of the roots of the first type of the beta equations doesn't vanish. But then in the second term, from the ratio of the hyperbolic sines from the beta equations, we're looking at the difference between roots of the first type and roots of the second type of the beta equations. And we're also having some parameters which are equal to the anisotropy parameters, but it's just times 1 times the anisotropy parameter in comparison to 2 times the anisotropy parameter, which appears in the first expression for the ratio of the hyperbolic sines, appearing in the right-hand side of the statement of the beta equations. And the following computation is necessary for obtaining an approximation for the local Hamiltonian. Namely, we're going to take the logarithmic derivative of the transfer matrix for the D23 spin chain under open boundary conditions, and we're going to evaluate about u is equal to 0. And we can have an expression for the summation of the eigenenergies of the local Hamiltonian, which is given by a summation over k which is given by 2 times the hyperbolic sine squared of 2 times the anisotropy parameter, which is normalized by the hyperbolic cosine of 2 times the roots of the first kind of the beta equations minus the hyperbolic cosine of 2 times the anisotropy parameter. And we can also obtain, as is listed in many references in the literature, which is good to include for demonstrating the connections between the eigenenergies and the length of the spin chain, is that we can obtain an expression also for the eigenenergies in terms of F naught, which is some force term, times the length, plus Fs, which is another force term, minus a term which is normalized in the length of the chain that's proportional to the Fermi velocity, which is given by a sine function, which is defined in the second line here, plus higher order terms, which are given by big O of the reciprocal of L squared. And the approximation for the transfer matrix that we're going to use for obtaining an expression for the open integrable Hamiltonian is given by the fact that we can express approximately the transfer matrix about the point U is equal to 0 in terms of a product of hyperbolic sine functions, which are proportional to the anisotropy parameters raised to the nth power, as well as an exponential of IP, where P, boldface P, denotes the one site propagator. So it just means that we move all the sites of the spin chain over by 1. We translate them by 1. And altogether, from some computations, which I demonstrate in the preprint that's going to come out, we can obtain an asymptotic approximation for the open integrable Hamiltonian, where the first leading term is proportional to the derivative, the logarithmic derivative of the open transfer matrix of the D23 spin chain, plus other terms which are given by an identity term raised to the tensor product of L, namely the tensor product of the length of the chain, as well as a hyperbolic sine term and 2 hyperbolic cotangent terms. And now I'm going to bring up again, as we had spent some time earlier in the presentation, going over the statement of the beta equations, which I just reproduced in this slide because it's going to come into play in looking at how the statement of the beta equation changes when we take the anisotropy parameter to be very close to 0. So recall that we had a dependence of the roots of the first type of the beta equation on the left-hand side of the equations, and on the right-hand side of the equation, we had a dependence of the equations in terms of the roots of the first and second type of the beta equations. And this is to say that, as we've been mentioning and alluding to, for anisotropy parameters that almost vanish, one can obtain an expression for the beta equations, which is given in the previous slide in terms of the following expression, which is given by removing the hyperbolic sine functions from all of the terms and obtaining this approximation for the beta equations, in which on the left-hand side, we still raise this ratio of roots of the first type of the beta equations to the nth power, whereas on the right-hand side, we still take a product from k is equal to 1 to m2, and another product from k is not equal to j to m1. And for obtaining a classification and making the connection with conformal field theory, we'll need to be looking at the logarithmic derivative of the beta equations for being able to characterize the density of the roots of the beta equation, which can ultimately allow us to obtain an interpretation of the ground state of the open boundary condition D23 spin chain, and how this relates to the the statement of the beta equations for low anisotropy parameters. So this is given by the fact that if we take the logarithmic derivative on the left-hand side of the beta equations, we can express the log of the absolute value of these 2 hyperbolic sine functions, which is raised to the length of the spin chain L for even L, as approximately L times a logarithm of the numerator term and minus a natural logarithm of the denominator term. And then whereas for the right-hand side of the beta equations, we can perform a similar computation to be able to obtain a natural logarithm and logarithm of these 2 products as we've been mentioning, from k is equal to 1 to m2, and k is not equal to j to m1, which can be approximately expressed as the logarithm of the first term plus the logarithm of the product of the second term. In the CFT sectors, which we've been discussing, is related to the fact that we can have a ground state, which is given from the eigenvalues of the Hamiltonian, which are satisfied when H1 and H2 are equivalently 0, whereas from the ground state, we can introduce three different types of excitations. Namely, we can look at one excitation, which is given by H2 is identically 0, but H1 is strictly positive, or we can have a type 2 excitation where H2 is strictly positive and H1 is identically 0. And finally, we can have a type 3 excitation to the ground state when H1 and H2 are strictly positive. And thanks for watching.